Morning students. Today's class we are going to study how a transistor acts as an amplifier and also a practical transistor amplifier using H parameter model. These two topics we will study today. First we will start how a transistor acts as an amplifier. In the previous class we have studied the need of amplification, different configurations of transistors. Now today we will see how a transistor acts as amplifier. So amplification is nothing but raising the strength of the weak signal to the desired level without any change in the frequency and shape of the signal. Raising the amplitude of the weak signal without changing the frequency is known as amplification. Raising or increasing the magnitude of the signal with the same frequency with no change in the frequency is called the amplification. The electronic circuit which increases the current, voltage or power of the weak signal without any change in frequency is known as an amplifier. Amplification is the raising the weak signal strength of the weak signal with no change in frequency is amplification. So electronic circuit which is used to increase the current, voltage or power of a weak signal without any change in frequency is called as amplifier. A circuit which is used to increase the current, voltage or power of a weak signal is called an amplifier. Is called as a amplifier. So we have accordingly the amplifiers are classified into different types. So current amplifier, if it raises the amplitude of the current, then it is called as current amplifier. If the amplifier raises the voltage of the voltage of the weak signal, if it increases the magnitude of the voltage, then it is called as a voltage amplifier. If it increases the power of weak signal, then it is called as a power amplifier. Later we will study in detail about these amplifiers: current amplifier, voltage amplifier in feedback amplifiers, and power amplifier in the chapter large signal amplifiers, power amplifiers. Let us see with the figure how the amplifier works here. So using the DC voltage as a source, the weak signal gets amplified. The amplifier here, see. So the amplifier first it works with a battery. It needs a supply DC voltage. So this is the DC supply VCC, it is required. So it is plus VCC, this is the plus VCC terminal. So here we are going to give an input signal. a small electrical signal coming from the loudspeaker is given as input to the amplifier. So the positive and the negative are connected as input to the amplifier. This is the negative, that is the ground, the positive terminal of the input signal given connected to the amplifier. Amplifier will work with the help of this DC voltage. The amplified signal is given to the loudspeaker. So this is the block diagram representation of an amplifier, how the amplification takes place. So actually the need of amplification, the voice of the singer reach everybody in the audience. If a public addressing system fails, so it is not possible to reach the voice of the singer to all the to the audience in the to the so we need a public addressing system that the voice of the singer should reach all the audience. So we need an amplification. So cannot we enjoy the cricket commentary on our radio with a low voice? No, it's not possible. So it is not application of amplifiers. We'll see the application of amplifiers in radio receivers, TV receivers, telephone receivers, because the received signal amplitude is very small, because all the way it comes from a long distance. The signals will be arrived from long distance, from satellite or from a antenna microwave receiver which is located at large distance. So by the time it received by the receiver, our receiver, the signal gets weakened because the propagation of path loss. So we need to before listening, the signal should be signal gets amplified. So we need a low noise. Actually in all the receiver, the first part is the LNA, low noise receiver, low noise amplifier. We need an amplifier in all the receivers. Stereo systems, public addressing systems, where we need a large sound output, we need a stereo systems. We are going to use the amplifiers. So the amplification, the active device which is amplifying the signal is the transistor, which is going to increase the amplitude of the signal, strengthen which raises the weak signal. The active devices are transistor or the field effect transistor will be used as active devices for amplification of the signal. It is not possible with passive devices, resistors, inductors and capacitors. Amplification is not only the active device like transistor or FET can raise the amplitude of the signal. So the main active device in the amplifier are the transistors or FETs, MOSFETs. Now MOSFETs only transistors and JFETs, junction field effect transistors. So before how the transistor is going to act as an amplifier, let us first start with the transistor. Transistor has two junctions, input junction, emitter, that is called as emitter base junction, and the output junction, that is called as collector base junction. There are four possible ways of biasing these two junctions. The four possible ways of biasing the transistor are fixed bias, collector to base bias, potential divider bias, that self bias, ultimate self bias. The transistor operates in a different uh, so since we have two junctions, uh, the input can be forward bias, emitter based junction and collector based junction. So we can operate the transistor in four different regions: active region, saturation region, cutoff region, and inverted region. So if emitter based junction is forward biased and collector based junction is reverse biased, the region of operation is known as active region. The transistor operates in the active region when the emitter based junction is forward biased and collector based junction is reverse biased. Input junction is forward and output junction is reverse. Then the transistor is in the active region. And in the active region, the transistor acts as an amplification amplifier. And coming to when the emitter based junction is forward biased and both collector based junction is also forward biased, and when both are forward biased, there is a low resistance to the flow of electrons, so huge current pass through the transistor and the transistor gets into saturation. So it acts as the transistor in the saturation region, and it acts as a closed switch, uh, conducting a large current because both junctions are forward biased, so it acts as a closed switch, and the transistor is said to be in the saturation region when both the junctions are forward biased. And when both the junctions are reverse biased, that is input junction, that is emitter based junction, and the output junction, collector based junction, both are forward biased, both are reverse biased, then the transistor acts as open circuit, no current flows through the transistor, so it acts as open switch. It is called as cutoff region, the region in which this transistor is acting as open circuit or open cutoff. It is called as cutoff region. When both the junctions are forward biased, it acts as a closed switch known as saturation region. When both the junctions are reverse biased, the transistor acts as a open switch, and the region is known as cutoff region. And when the input junction is reverse biased and the output junction is forward biased, it is called as inverted region, and it acts as a overload. So the configurations of a transistor, because we have three terminals for the transistor and making one terminal as common between the input and output, so we have we can since the common, we can made any of the three terminals, emitter, base and collector. So accordingly the transistor is named as can be worked in three configurations: common emitter configuration, common base configuration, common collector, making either one of the terminal as common. So accordingly that transistor is named as transistor has three configurations: common base configuration if the base is common, common emitter configuration if the emitter is common, and common collector configuration if the collector is common between the base and emitter. So the transistor works as an amplifier uh, in the CE configuration, mm, and CC configuration actually it works, it will not going to amplify the voltage. So we'll see there are parameters which are going to be increased in the different in three configurations: CE, CB and CC configurations. So in CB configuration, common base configuration, the current gain is not possible, and CC in the voltage gain is not possible. CE we can achieve both, yeah, current and voltage gains are possible, so it is the widely used configuration when comparing with the CB and CC. So CB has a high voltage gain, but it has no current gain. Current gain is less than unity, and CC we have a high current gain, but no voltage gain in common collector configuration. In CB we have high voltage gain but no current gain. So CB we have a unity current gain, and CC we have a unity voltage gain. So it is not possible the voltage gain and current gain simultaneously with the CB and both at the with the CB and CC configurations, but we have current and voltage gains both are possible with the C configuration. Hence it is widely used configuration. C is the widely used configuration of the three among the three configurations: CB, CE and CC. C is the widely used configuration. So the faithful amplification, so the output amplified signal should be in should be similar to the input signal, that is called as with no distortion. So the faithful amplification, regardless of the polarity of the input signal, the emitter base junction must be forward biased, and the collector base junction must be reverse biased for faithful amplifier. That is, the transistor must be operated in the active region. So we will get the faithful amplification is possible when the transistor is operated in the active region. For the faithful amplification, the transistor need to operate in the active region, where it acts as an amplifier. If it operates in the saturation or cutoff, there is a signal will be clipped during the positive or negative off cycles. When the transistor goes into the cutoff region, negative peaks will goes off, and when the transistor goes into the saturation, positive peaks will be clipped. So the output signal not exactly similar to the input signal. So it is called as a distortion. So to avoid distortion, it should operate in the transistor should be operated in the active region only for amplification. So we have the different notations for voltages and current. IEEE standard notation for different voltages and currents, for representing the currents and voltage in a transistor. Capital letters are used to indicate the DC values, RMS values of AC current, and the DC values of voltage and current, the capital letters. Small like capital I for current and capital V for the voltage. So it is the capital letters are used for representing the DC values and RMS values of AC current. Small letters are used to indicate uh, the instantaneous values of current, voltage, small I for the current and small v for the voltage. So small letters are going to be used for the instantaneous values of the voltage and current. And the small letters with the capital subscripts. Small letters like small I with capital subscripts B, capital B. Average values and instantaneous total values are represented with the small letters with the capital subscripts. Average values and instantaneous total values are going to be represented with the small letters with the capital subscripts. Like example, base current is represented small I subscripted with the capital B. Magnitude of the DC supply, like double subscripts for the proper electrode symbol, BBB DC supply in the base circuit, VCC DC supply in the collector circuit. See, these are the notations, IEEE standard notation for different representing the voltages and currents in a transistor. So this is the figure showing the transistor connected in the CB configuration. So base is common here. The base terminal is made common between the emitter and collector. Here the base terminal, this is the base terminal, which is going to be common for the input and output side. So input side we have emitter and the output side we have the collector. So this is the input junction, input, and this is the output junction. So collector base junction is the output junction. So this is the base terminal is common between the emitter and collector, so it is called as common base configuration. See the C circuit of C amplifier here. Circuit of C amplifier. So this is the circuit of common C amplifier. So we have two biasing voltages, VBB and VCC, to fix this transistor, NPN transistor in the active region. So how this transistor, NPN transistor, is in the active region. So this VBB keeps the input junction forward bias. This VBB keeps this input junction forward bias, and this VCC we are going to keep the output junction, collector base junction, that is the collector base junction, output junction in the reverse bias. This is the output junction, the reverse bias using this supply VCC. This output junction is in the reverse bias, and the input junction, this VBB keeps the input junction forward biased, so that the transistor, NPN transistor, works in the active region. Circuit of C amplifier. So the emitter terminal here, they are made common between the base and collector, so it is called as a common emitter configuration. So in the C amplifier, because it is widely used, we are going to discuss the transistor, how it works as an amplifier, by considering the CE configuration. CE amplifier circuit. The weak signal is that is to be amplified is applied between the emitter and base junction. The signal to be amplified is applied, that is the weak signal that is to be amplified is applied between the base and emitter junction, So this is the signal that is applied between the base and emitter of the transistor. The output is here the output is taken across the load RC here. So we have the voltage, this is the output voltage, this is the output voltage. So the output voltage is taken. So the output voltage is taken across the load collector resistor. We are giving input here, and the magnitude output amplified signal is obtained across this RC voltage. The VBB is applied in the input circuit to keep the emitter base junction forward biased, regardless of the polarity of the input signal, whether the input signal is going in a positive cycle or negative half cycle. The VBB will fix the input junction, that is emitter base junction, in the forward bias. The input junction of the transistor is kept in the forward bias condition using the VBB, power supply VBB. VCC applied to the reverse bias is used to reverse bias the collector base junction, VCC. And now the transistor is going to be biased in the going to operate in the active region, that is biasing. The transistor is biased to operate in the active region. The operation of an amplifier, principle of amplifier. When the input signal is applied, base emitter voltage varies with the time, because the signal to be amplified is an AC signal. So when the input signal is applied at the base emitter voltage applied, so the base emitter voltage VB is varying with the time, because this is the input signal that is applied at the base and emitter terminal, between the base and emitter terminal. So with the change in the signal with the time, so the voltage VB also going to vary with the time. The input voltage, the input signal is applied when the input signal is applied, the base emitter voltage VB varies with the time. So when the base voltage is varying with the time, this base emitter voltage is varying with the time. So the base current IB is also varying with the time. When VB is varying, the the IB is also going to change with the time. So when the base emitter voltage is changing with the time, the base current also going to change with the time. So when the input signal is applied between the base and emitter, the base emitter voltage VB is varying with the time. It varies with the time, according to the input signal. The VB varies with the time. So the base current IB also varies with the time, because the current depends on the voltage. So when the input voltage VB is varying, so the base current is also going to be varying with the application of the input signal. This varying base current passes through the so since the base current is varying, the collector current also varies, because because the collector current depends on the base current. So when the base current is varies, similarly the current is collector current also varies with the time. This varying current passes through that collector current. The varying collector current passing through the RC, and varying voltage is developed across the RC. So this varying IC collector current, in accordance with the base current, the collector current also varies. This varying collector current, when passing through the collector resistor RC, it is going to produce the varying output voltage across the RC. Here the output voltage is many times greater than the input voltage, because the output may have high resistance because the junction is reverse biased at the output side. So the output may have high resistance. So when the current is passing through this high resistance, when a current is possible to pass through this high resistance, we are going to produce the large voltage is going to be produced at the output side. So see the understanding how BJT circuit here. So here the increasing symbol is represented with the increasing and decreasing symbols are representing with the increasing and decreasing voltage is represented with the blue arrows, and increasing and decreasing current is represented with the red arrow, and also the horizontal arrow direction of the current. See, when the input voltage is increasing VBE, so the input current IB also increases, upward arrow. When VB increases, IB increases. So when IB increases, IC also increases. IC increases. So when IC increases, VCA decreases, but where it going to increase the IC, then this IC when flowing through the load resistor, it is going to produce a high voltage. When passing through the load, then this increase in the collector current when passing through when it is passing through the load, it is going to produce the voltage, a large voltage. During the operation, let us see during the positive half cycle of the input signal, the effective forward bias across the emitter base junction is increased during the positive half cycle of the input signal, because the signal to be amplified is AC. So during the positive is varying with the time AC signal. So during the positive half cycle of the input signal, the effective forward bias across the emitter base junction is increased. So we have already the input junction is forward biased, and the input signal to be amplified is also is positive, going positive. So we have effective forward bias across the emitter base junction is increased. It causes the increase in the collector current, and it going to increase the collector current. Both the forward bias and the positive going half cycle of the input voltage going to increase the base current, and therefore more forward bias, effective forward bias going to increase at the input. So therefore the collector current increases. Hence greater the voltage drop across the collector load RC. so that voltage more drop will occur, more voltage drop appears across the load resistor RC, because the collector current is flowing through the load resistor. During the negative half cycle of the input signal, the effective forward bias across the emitter base junction is decreased. Though the input junction is forward biased using VBB, but the negative going off cycle of the signal to be amplified, the input signal, going to decrease the effective forward bias at the input junction, so it is going to decrease the base current and hence the collector current. So it causes decrease in the collector current during the negative off cycle, hence the decrease in the output voltage. So we have during the positive half cycle of the input signal, the magnitude of the output signal is increasing, and during the negative half cycle the output voltage is decreasing. So we have the voltage, the small signal to the input and output get bigger output. So we have the current is in phase here with the input. The total collector current here, we have a DC current IC, zero signal collector current, that is the biasing current IC. Small IC is the AC collector current. So the total current, collector current, small I capital C, that is the total collector current, is the sum of the AC collector current small I small c subscripted with small c and plus the DC collector current, DC value of collector DC value of current, collector current, that is capital I capital C. So that is represented in this waveform. See here, so here we have this dotted line indicating the DC current. This DC current IC already is kept at some value, some above 0 value. This is the value fixed by the DC biasing circuit VBB, and with the help of some resistive circuit it fixes the DC collector current at this value before the signal is applied. This is the signal before, not at that time only. When the signal is not applied, then we have that value, we have a current in the circuit, that is the DC collector current, because of the biasing voltage. So when that is called as zero signal collector current, because the signal amplified is not applied, so we have a current in the circuit because of the biasing voltage. So this is called as the DC collector current because of the biasing voltage VBB. And when the signal is to be amplified is applied, so that signal is varying above and below this DC value of the collector current. So when during the positive off cycle of the input signal, the collector current, the DC, the AC, this is the amplified collector current, AC collector current. This AC collector is collector current small I and capital small I, and the total collector current, that's capital C, is varying above. This is the current small I small c. So this is the AC current is varying above and below the DC current. So now the total current, this is the total current. So this total current is varying with the time. So this is the sum of, now this total current, the total current is the sum of this is the total current. This is the total current on the y-axis, which is the sum of the AC waveform, AC output current, and this is the steady state zero signal DC current. So shown in the dotted line, this is shown in this capital I and capital C shown in the dotted line, and this is a small waveform which is varying above and below this value. So this is the IC, the total current, which is shown on the y-axis, which is the sum of the AC collector current and the zero signal DC current. The total current is the sum of the AC collector current and the zero signal collector current, DC current. So similarly we have the voltage. So the output voltage VCE, total output voltage VCE. VCE is the collector to emitter voltage. Small v and capital CE is the total signal large output voltage across the collector emitter terminal, which is the sum of the DCC. Here we have the three waveforms. This is the output voltage. So here we have initially we have a DC voltage. This is a DC voltage VCE, and this DC voltage, and this is a small AC output voltage across the RC. Small signal or AC signal here. So this signal, the output signal, this signal is going to vary with the collector, AC collector current that is flowing through the resistor RC. So this is the voltage drop that is produced across the RC. It is called as VCE, AC voltage produced due to the collector current, which is passing through the resistor RC. So this will going to be decrease with increase in the current, and increases with the decrease in the current, opposite phase to the current, output current. So therefore, so when the input voltage is this waveform is this is the waveform which is overlapping above and below this DC, going to produce this value DC voltage. So these two, when combining 1 and 2, when combining, going to produce 3, the waveform 3 shown in the graph. So the input signal here before amplification, the input voltage is like this, but we have the output signal after amplification, the magnitude, large magnitude of the output signal here shown in the dark portion. This is the output signal, large amplitude of the output signal. There is a phase shift of 180 degrees between the input voltage and the output voltage, because when the input, with the increase in the magnitude of the input signal, when during the positive half cycle, we are going to increase the positive half cycle of the collector current increases during the positive half cycle, but the collector to emitter voltage decreases during the positive half cycle of the input voltage. So there is a decrease in the voltage during the positive of the output voltage during the positive half cycle of the input signal. So there is a decrease in the amplitude of the, so the output voltage is going to be negative half cycle for the positive half cycle of the input. So there is a phase shift of 180 degrees between the input voltage and the output voltage, input signal and the output signal. So this is the CE amplifier where we are going to get a phase shift of 180 degrees between the input and output voltages. Coming to the important points, salient features of CE amplifier. So it is going to have a moderately low input resistance. Because the input junction is forward bias, it is going to have a low input resistance of the order of 1 to 2 kilo ohms. Input resistance of the CE amplifier is going to have a moderate input resistance. C amplifier is going to have a moderate input resistance because its input circuit is forward biased, so the input resistance is very moderate value, that is 1 to 2 kilo ohms. Moderately high output resistance because the output junction is reverse bias, so we have a output resistance which is almost it is equal to 50 kilo ohms, and it is going to have high current gain, very high voltage gain. Both high current gain and voltage gains are possible, and also high power gain. So because the voltage, and it is going to have increase the voltage and current signal, so we have high power gain. Power gain is also possible with the CE amplifier. And also the input and output signals are 180 degree out of phase. So we have a phase shift of 180 degrees between the input and output signals. Comparison of 3 configurations. Comparison of the parameters: current gain, voltage gain, power gain, input impedance, output impedance, and phase shift. Current gain is nearly unity in the CB configuration, but we have a high current gain with the CE, and a very high current gain is possible with the CC. And voltage gain so current gain is unity in the common base configuration. And current gain is nearly unity. So means there is with the CB configuration it is not possible to increase the current, but we can increase the current using CE. It is very high, it is going to increase the current gain of C amplifier is very high, and CC configuration is very high. Voltage gain is not possible with the CC configuration, nearly unity, common collector, but we have a high voltage gain possible with the CB and very high voltage gain with the CE. And coming to power gain is high in CB and CE, but not possible with the CC. Power gain also not possible with the CB, only it is possible with the CE, because it is the configuration which have both voltage and current gain, so it is going to have a high power gain, but power gain is not possible with the CB and CC configurations. Input impedance is very high. So input impedance is common base configuration. Emitter is the input terminal, so emitter is a heavily doped region, so it is going to have a very low input impedance CB, and because for CB emitter is the input terminal, emitter is heavily doped, so it's going to have low impedance of all the three. And CE, for CE the configuration, base is the input and base is moderately doped, so we have a then high input impedance, and the CC we have very high, because for CC configuration, common collector configuration, base is common collector emitter is the output, and base is the input terminal, and it is very lightly doped. So input impedance, low input impedance in the CB and high in the CE, and very high in the CC configuration. Output impedance is very high in the CB configuration, and CC we have a very low output impedance CC, because in the CC configuration emitter is the output terminal, so emitter is the output terminal, so it is lightly doped, so we have very low output impedance in the CC configuration. So when the output resistance is very low, it is not possible with the voltage gain. It is not possible with the voltage gain. When the input resistance is very high, input impedance is very low. So phase reversal only we have possible with the CE configuration. There is no phase shift between CB and CC configuration. So coming to the configuration, which is the best suited as an amplifier, why the CE configuration is widely used in amplifier circuits. So it has high input impedance and both input impedance and output impedance are moderately. We have moderate input and output impedance, and voltage and current gains are possible with the CE configuration. So we have a high power gain, which is not possible with the other two configurations, CB and CC. So it is possible only with the CE, the voltage and current signal both we can amplify. So we have a power gain with the CE configuration, hence it is a widely used configuration. CE is the widely used configuration. So the summary, today's class we have discussed about the need of amplification. Why do we need an amplification? Application of amplifiers in different applications of amplifier, operation of a transistor as an amplifier, how a transistor is acting as an amplifier, configurations of a transistor, and the regions of biasing of transistor, different regions of operation of transistor, and how the transistor is acting as an amplifier, and different regions of operation of transistor configurations, and advantages of CE amplifier, and comparison of CE, CB and CC configurations. In a transistor, let us see some small questions, quiz questions. In a transistor, the signal is transferred from low resistance to a high resistance to low resistance, low resistance to high resistance to high resistance, low resistance to low resistance. So the signal is transferred from a low resistance to high resistance because the input resistance is input junction is forward biased and output is reverse biased. So we have a low resistance at the input and high resistance at the output. So signal is being transferred from low input to output, so low resistance to high resistance. That is answer B. Which region the transistor acts as an amplifier? Cutoff region, B saturation region, C active region, D all of the above. So in the transistor acts as an amplifier in the active region. In the cutoff and saturation region, it acts as a switch. Cutoff region open switch and saturation region closed switch. So in the active region, it acts as an amplifier. Answer is C. Which of the following configuration provides highest power gain? CC configuration, CE configuration, CB configuration, none. Since CC configuration, voltage gain is not possible, and CB configuration, current gain is not possible. So when both current gain, voltage gain are possible with the CE configuration, so we have a power gain. So CE power is the configuration which is going to have high power gain. CC and CB, it is not possible. So answer is CE configuration. The phase difference between the input and output waveforms of CE amplifier is 270 degrees, 180 degrees, 90 degrees and 0 degrees. So we have a phase shift of 180 degrees. When the input is going positive, we are going to get a negative half cycle of the output voltage. So we have a phase shift of 180 degrees between the input and output voltage with a CE amplifier, 180 degrees. B. CE circuit is also called dash circuit. Grounded emitter, grounded collector, grounded base. Grounded emitter circuit, because the emitter is grounded, so it is grounded emitter circuit. Questions coming frequently on this topic are: what is an amplifier? What is an amplifier? Draw the circuit and explain the operation of transistor as an amplifier. Compare the three different configurations of transistor. So today we have studied how a transistor acts as an amplifier, the different configurations of transistor, and how a transistor is amplifying the signal, and the comparison of CE, CP and CC configurations of transistor. So we will stop here.